All right. Now we're talking
Perfect.
about, okay, lecture 5B, Muller et al., chapter 3, industrial minerals. So these are the elements that we've been talking about. It's a lot of elements. They're all found in the continental crust right now, and in crust-derived sediments, and tremendous variations in the mean abundance. 11 orders of magnitude are shown here. So that's not the abundance in individual ore deposits. That's just the average abundance in the crust, and then continental crust. And then you can see the major industrial metals are in red, right? These are things that are usually on the left-hand side of the periodic of this, left-hand side of the atomic number chart, except for lead, because lead was created by uranium decay and as well. And then the precious metals are in purple. Let's see what they're considering with precious metals. Don't see them. And then rare earth elements are in blue. So a confusing constellation. And then they include yttrium and scandium in the rare earths. So anyway, there's a lot of detail in this chart, which is, we're just talking about mean abundances in the continental crust. All right, so this chapter organizes metals by crustal abundances into 5 groups and discusses how they are used. So the rest of the book follows this structure. There's a number of ways to subdivide the elements that we're going to talk about in minerals and metals. And the least scientific one would be just how abundant they are, right? As a scientist, I would have preferred to have organized it by similar processes, but there's advantages in doing it this way too. So there are these 5 categories, count them, 5. There's abundant metals, there's scarce metals, there's rare metals, there's trace metals, and there's precious metals, right? And everybody loves gold. Gold's our favorite metal. If you have to, I suspect if you went out and took a poll of the average person, like Jay Leno used to do, for those of you that remember Jay Leno, what's your favorite metal? People would probably say gold, but the abundant metals, the scarce metals, the rare metals, the trace metals. I have some problem distinguishing these 3 groups, right? Abundant metals, I have no problem. Precious metals, I have no. Well, we will see there is a little bit of a problem with precious metals, because the question is, it definitely includes gold, but what else does it include, if anything? But scarce, rare, and trace, it's like, okay, I'm not sure I understand the difference, but they define it basically on the crustal abundances. So abundant metals have abundances of more than 100 ppm, parts per million, in the continental crust. Scarce critical metals between 10 and 100 ppm. Rare critical metals, 10 ppm to 1 ppm. Trace critical metals, less than a ppm to 10 parts per billion. So, like, if you think about this class, there's about 10 of us. We're about a part per billion of the world population. So that gives you an idea how small a part per billion is. Actually, maybe 1.5 ppb of the world population. And then, of course, we've got gold and silver. And gold is at 4 parts per billion in the continental crust. That's damn little. So we'll go through you take this classification, and we will go through it, how we use these elements. So here is a periodic table. Now what we've done is we've colored the elements that are going to be considered. Things in white the book doesn't consider, so we won't spend much time thinking about them either. But so let's see, the abundant ones are in purple, right? So these are 2 abundant ones, right? There's the pink abundant and there's a purple abundant. Things that are really abundant are in purple. Things that are just kind of abundant are in pink. And you can see they're all sort of near the top of the periodic table, except for barium. And then we got critical metals, and they're, lithium and this side of the transition elements, lead. So there's critical, these are scarce ones in the orange, and then there's rare ones in the yellow, which are now we're moving down the periodic table, and that's including the rare earths. It changed its own. And then there's these trace critical metals. There's only 4 of them. So it's a relatively short chapter. And then, of course, we're missing the precious metals. Interesting. There's these are the trace. Interesting. It's not the precious metals. So it's a little bit confusing, but you can see that this is a confusing periodic table, but that's kind of the way we're going to go through it. What's that?
I just said the precious metals.
Oh, you're doing like Lord of the Rings accent? Is that what that is? My precious? No? Okay. So anyway, we've done that. So let's talk about the abundant metals first. I will circle in red the ones that are abundant, and we're going to go through all of these elements and just talk about how we use these metals in civilization.
Madison's got her hand up.
Oh, okay. Please.
I was just wondering how this was determined. Like we haven't obviously ground up all of the crust. So how do we have these estimates of what the kind of average concentration?
Scientists make their name by publishing papers, and they really make their name when they have a highly cited paper. And there's these big overviews of this and that are the most highly cited. So Rudnick and Gow is, maybe has 10,000 citations, which is astronomical for a scientist. And it's because it's a geochemical summary of the continental crust based on, you'd have to go into the paper, but there's a number of people that have done this kind of an exercise and to basically give us these estimates of what's in the crust. And so it's coming from the peer-reviewed scientific literature. Is it flawed? Absolutely.
General agreement, or are there kind of differences?
Well, I mean, you're not going to get 10,000 citations if people don't find what you've done useful. I mean, because nobody's going to write a paper about how wrong you are. There'll be a few curmudgeons that will do that, but by and large, the age of the discussion and reply is over. We used to be when there were fewer papers published, people had more time to talk about them. Now that everybody's, pedal to the metal, publish everything you can as quickly as you can. Nobody's got time to do a discussion and reply. But I would have to say that these highly cited things to the first order are broadly correct. So if now, number one, let's go back. This is a log scale, and it's 1, 2, 3, 4, 5 cycle. No, that's not true. That's 15 log cycles. So anytime you plot something up on log paper, even if you're off by a factor of 2, you're right. Right? The best correlations are log plots because things tend to line up on a straight line. And we've talked about how we estimate the total abundances in the earth, and then that constrains our understanding of what must be in the continental crust. So this is a useful compilation, even though in detail you could go into it and go, oh, you're completely off on, say, tellurium or something like that. I don't know. You'd have to pick the element that you want to, the hill you want to die on, I guess. So they're useful. So let's start moving through the abundant metals. We got 10 of them we're going to talk about. And aluminum is number 1 in the book. I'm not sure how they organize this. It may be alphabetical. But aluminum is very popular because it's readily recycled, and it has good physical properties. Its versatility, conductivity, tensile, that should be tensile strength, strength to weight ratio, malleability, flexibility, durability. Everybody loves their aluminum foil. I mean, what metal can you use and throw away like that? And so it's just a very flexible metal, and they're aluminum used in high-rise construction, consumer electronics, window and door frames, industrial and household appliances, power lines. I did not know this, but most of the high power lines are made up of aluminum wrapped around steel, in airplane and spacecraft components and in vehicles. So it's a very valuable, useful metal. And here, this chart, we'll come back to it over and over again. So here's iron, that's 94% of everything we mine. And there's aluminum sitting there at number 2, being enviously regarded by manganese ore, which is right underneath that. So now this is, I think, 2019 or 2020 chart. Nothing really has changed too much. The next one is phosphorus. Now phosphorus is interesting because it's not used like metals are used, and it's mainly used in fertilizer. And we talk about the Green Revolution and how the Club of Rome was wrong about people starving because people started using more phosphorus in fertilizer. So yes, John. You got a question?
Yeah, Matthew, I was just curious. I mean, I really know Canada's got tons of aluminum. We bring it all in from there. Where are the aluminum deposits in Canada?
I'm not
No.
sure Canada's a big aluminum.
No, we're a big phosphate.
No,
Yeah,
they're
lots.
big. All the aluminum that comes into the U.S. is basically mined and processed in Canada. Pretty much shut down the U.S. industry.
It might be processing because Canada's got a lot of inexpensive electricity because of their hydroelectric, but let's dig into that a little bit more in the future.
Okay.
I understand that the Columbia River, at least in the past, there was a lot of aluminum processing done up on the Columbia River in the US. I don't know if they still do it. But where they get it is, I mean, it comes from like bauxite.
Yeah, we'll get into that. We'll get into that. Right now, we're just talking about how we use it. So the third one is titanium. Titanium and especially titanium oxide have a wide range of uses: commercial, medical, and industrial. Commercially, titanium oxide is a permanent pigment, right? They used to use lead in paint. Now they replace that with titanium oxide because it's nice and white. It's also used as a strengthening agent in steel helmets or golf clubs that are composed of graphite. In the medical industry, they're used for surgical and dental implants, as titanium is biocompatible, right? You're always worrying about things breaking down in your body. Yes, Clint.
White titanium paint doesn't taste nearly as good as lead paint, though.
Thank you for that insight.
And
That
lead
explains-
paint actually
that-
does taste good, which is
That
why children hate it.
that explains a lot. Titanium, okay. Lots of titanium in the medical industry and industrial use.
Madison.
Oh, okay, Madison, go ahead.
I was just wondering, they talk about how titanium makes plastic and pigments more chemically inert, and I was wondering if you kind of understood the mechanism of that, as well as how it's able to absorb UV light, but letting visible through. don't know
I
if that was
do
too off
not.
topic.
I do not,
Okay.
and maybe somebody else does.
Not me.
Apparently not. So, Madison, good question. You will find in this class there are many good questions we are incapable of answering. But to our credit, we will say so. Other people might not. I hope it's to our credit. So, titanium is fairly lightweight, and it resists temperatures as high as 1,000 degrees Fahrenheit. I suspect even higher than that. Maybe that was supposed to be centigrade. used in all kinds of airplanes, spacecraft, armor plating, naval vessels, normally alloyed with aluminum, iron, zirconium, moly, nickel, or manganese to include its strength, also used as an additive in the pulp and paper industry due to its resistance against corrosion. All kinds of interesting uses that I never imagined. Abundant metal number 4 is vanadium, the easiest element to remember from its initial. 80% of all vanadium is used as a steel additive. So vanadium steel alloys are very tough, used for armor plating, axles, tools, piston rods. Less than 1% of vanadium, in addition to chrome, makes steel shock resistant and vibration resistant. Used in nuclear reactors because of the low neutron absorbing properties of the metal, and vanadium oxide can be used as a pigment for ceramics and glass, as well as catalysts and in the manufacture of superconducting magnets. Almost sounds like a material science class. Abundant metal use number 5 is chromium. So this one is interesting because 80% of our chrome comes from one layered intrusion in Africa called the Bushveld, which we'll talk about a couple of times in this class. The main element that hosts it is called chromite, which is a spinel for those of you that know their minerals. Chromium's very versatile metal, and the metal markets distinguish between metallurgical, refractory, and chemical chromium ore. So for metallurgical ores, chrome grades of less than 45% Cr2O3 are usually rejected at the mills, and a certain chrome iron ratio is preferred. For refractory ores, a coarser grained chromite is preferred, and the chrome content could be low as long as aluminum content contributes to at least 60% of the ore. For the chemical ores, chromite must be fine grained and chrome content can be very low. Used in a wide range of things there: metallurgy, electroplating, production of stainless steel, plays an important role in various alloys. Chrome is used as a thin film coating on semiconductors to enhance their conductivity and protect them from corrosion. Also used in producing magnetic tapes and hard disks. As heating element, chrome nickel alloys are used in heating elements and electronic devices. Chrome also plays an important role in cast iron. Chrome iron alloys have improved hardness, wear resistance, and corrosion resistance, which makes them very useful in manufacturing engine blocks, cylinder heads, and other automobile parts, and is also added to brake pads to improve their performance. Added to pigments, used in refractory materials and catalysts. Important in producing chromic acid, chromium salts, and chromium compounds in general, and are used in leather tanning. We don't want to forget about that. So where's chromium down here? There we go. That's number 4 in the amount of material we use. Manganese, number 6 of the abundant metals. 90% of manganese, and people get confused between magnesium and manganese, but because they both have an M and an N and a G, but manganese and magnesium, yeah, you're just going to have to get used to it. Mn is manganese. So 90% of manganese consumption is used in steel. Mag alloy is about 14% manganese. Globally used in producing low-cost stainless steel, makes it very important for the automotive industry. Manganese copper alloys are used in shunt resistors to measure very strong currents. Non-ferrous applications of manganese include producing dry cell batteries, plant fertilizers, animal feed, and as a pigment and colorant for ceramics and glass. Manganese additives are used in gasoline to increase the octane rating and decrease engine knocking. I guess It's kind of like lead used to be used. And manganese is, number 3 here, right after aluminum and ahead of chromium. Iron, now the iron is king. Iron is 94% of all of the metals we mine. Most iron ores consist of iron oxides, 98% of which are used to make steel and steel alloys, with about 2% used in inks, catalysts, and paint. And then I learned there's 6 types of processed iron. There's white cast iron, there's carbonyl iron, there's wrought iron, there's soldering iron, there's pig iron, and there's cast iron. So white cast iron is a very brittle product, which makes it useful in constructing ball mills, extrusion nozzles, cement mixers, pipe fittings, pump impellers, and crushers. Don't ask me to explain why anything brittle would be useful for that. Carbonyl iron is used in the electronics industry to manufacture magnetic cores of high frequency coils and broadband inductors that are stable under a wide range of temperatures. Wrought iron is an alloy of steel with carbon, which has excellent ductility and corrosion resistance, used in gate and fencing industries, as well as in home decors. I think you've all seen wrought iron table stands, pot stands, and wine racks. Probably all of us have some of that in our homes. Soldering iron, we use that for repairs. Pig iron represents an intermediate product during the production of steel. So we haven't talked about steel yet. We're just talking about iron. Cast iron is made by combining iron with about 2% carbon, and it has a low melting point temperature and high strength and ductility, which makes it useful for electrical fittings, hand tools, washers, brackets, and machine parts. So, like you can see, iron is basically, 94% of the mining we do. Abundant element number 8 is zirconium, and with it, hafnium is its geochemical twin. There may not be 2 elements that are more similar geochemically than those 2. And basically we find zirconium and hafnium in the mineral zircon. We talk about zircon a lot in geology, generally not because it contains zirconium, but because it's used for isotopic measurements, things like that. And it's mainly used in ceramics, refractories, foundry materials, chemicals, and abrasives. Especially important in the glass industry, where the linings of glass furnaces are made from a combination of zircon and zirconia bricks. Also used for preparing molds in the casting of metals. In the chemical industry, used in paint dryers, paper coatings, antiperspirants. Did not know that, but also for leather tanning and flame proofing. So zirconia is also used in abrasives, right? Zircon is a very hard mineral, and specialized uses in glass and electronics, and in coating the faceplates of cathode ray tubes. Barium is mainly used in the petroleum industry, in drilling mud, but also in the steel industry, electronics industry, and in medicine. In medicine, everybody knows about barium. We use it as a contrast agent when we're trying to get radiographs of the gastrointestinal tract. And barium compounds are used in manufacturing plastics, rubber, electronics, steel, textiles, ceramics, glass bricks, paper, pharmaceuticals, toothpaste, and cosmetics. And barium chloride is useful in a lot of things too. And our last abundant metal is graphite. Now, graphite is kind of interesting because graphite, everything we've talked about here has been a metal. Now we're talking about a mineral, which is just made of carbon. So natural graphite is widely used in electrodes, refractories, lubricants, foundries, batteries, steel production, and friction products such as brake linings. But it's becoming increasingly important because of graphene, which is single layered carbon, which is a new material that's being developed for a wide spectrum of high-tech applications. It was first isolated in the laboratory in 2004, and it's basically provided a new dimension to materials research and nanotechnology. It's still a laboratory material, but there's a lot of research on how we can move it into the industrial realm. Graphene exists in several forms, such as nanoribbons, nanosheets, nanoplates, and 3D graphene, each of them potentially offering a wide range of industrial applications. Lots of people doing research on that, including at our university. Let's watch a video.
Graphene is an amazing material, yet it was only discovered in 2004. This is the thinnest light bulb, and it's made from graphene. This is Materials Lab, and is graphene a wonder material?
Graphene is my best bet for the next disruptive technology.
Graphene is a single thin layer of graphite, the soft flaky material used in pencil lead. A diamond and graphite are forms of carbon, yet they have widely different natures. Diamonds are incredibly strong, while graphite is brittle. Graphene's atoms are arranged in a hexagonal arrangement. So, when graphene is isolated from graphite, it takes on some miraculous properties. It is a mere one atom thick, the first two-dimensional material ever discovered. Graphene was discovered by Andre Geim and his students. Geim set Dajiang the task of obtaining as thin a sample as possible by polishing a 1-inch graphite crystal. During research, Geim and a PhD student named Konstantin Novoselov discovered that graphene had a pronounced field effect, the response that some materials show when placed near an electric field. This would then go on to earn Geim and Novoselov a Nobel Prize in Physics in 2010.
This prize so very special. From the very bottom of my heart. Thank you all.
Silicon is defined by its ability to field effect, and many researchers believe that graphene could replace silicon because of this.
We have developed full technology of a graphene-based magnetic field sensor. This sensor were produced of graphene on silicon carbide.
Research into graphene was ignited, and scientists across the world were startled by their findings.
We started to see it first in composite material applications, in sport goods. Now it goes into advanced cars, but now we already start to see it being used for electronics, for printed electronics.
It is one of the thinnest materials known to man, yet it was 150 times stronger than an equivalent weight of steel. It is as pliable as rubber and could stretch to 120% of its length. Unfortunately, it does come with some negatives. For example, graphene cannot be turned off. A device that cannot be turned off consumes way too much power. The electrons go super fast thanks to graphene, but it can't be turned off. Some scientists believe that the real issue is business. Silicon is the go-to material for semiconductor chips, and the industry is based around this. For graphene to become the norm, then it first needs to work with silicon in existing production lines. Outside of semiconductor use, graphene has been used in bulletproof vests that had twice the stopping power of a Kevlar vest, or 10 times better than a steel plate. Batteries were capable of charging to full in 5 seconds. Researchers have developed graphene-enabled electrochromic glass that can switch between solar heating and radiative cooling modes. Our device has one of the largest tuning ranges in thermal radiation ever demonstrated. Po-Chun Snu, materials scientist, Duke University. Graphene has been found in the concrete industry. Scientists at the University of Exeter developed a new method to add the material to conventional concrete.
We learned here at Exeter recently how to combine the lightness and the stiffness of graphene into an ordinary material like concrete to make a new form of concrete that goes under the name of concrete. And that's what we are talking about. We have a new kind of concrete that is lighter and stiffer than normal concrete.
The technique is to add water-stabilized graphene dispersions to a concrete mix, resulting in a material with double the strength and 4 times the water resistance. Even though graphene is being researched in multiple areas, its cost is still high. The price of graphene can range anywhere from $100 to $450,000 per pound. This, of course, depends on the quality. Unfortunately, not all graphene is created equal. You can, of course, have lesser quality for cheap, but the best is required for the advancements we seek. In the future, graphene could become the wonder material that many scientists believe it has the potential to be. We will just have to wait and see what happens.
So it's not a big surprise that, people are increasingly interested in graphite deposits. It's not just pencil lead like I thought it was before I started working on this lecture. So anyway, here's another table in your book. The blue shaded fields mark the most important industrial applications of the different materials. Oh, I forgot ammunition under phosphorus, fertilizer, food. So, So the chapter goes on to talk about scarce critical metals, which includes nickel, copper, zinc, lead, cobalt, lithium, and gallium. They have crustal abundances between 10 and 100 ppm, and that we'll get into that in chapter 5, right? We're going to spend more time talking about each of these, how the deposits form. Right now, we're just talking about how these elements, metals, are being used. So let's get on to the critical metals, scarce critical metals, the orange things, right? 5 of them in the periodic table in the transition elements, and then gallium, lithium, and niobium, lead. And they're including these rare earths for some reason. They're not they've separated these rare earths out of them. Okay. So let's go through the 7 scarce critical metals. Nickel. So nickel alloys with a wide range of metals. Most important ones are the ferrous alloys, including stainless steels, low alloy steels, cast irons, and some specialty steels used in gas turbines, chemical plants, etc. So this is breaking it down. Most of it is used in ferronickel for stainless steel, and then non-ferrous alloys, other steels, things like that. Now, number 6, it's only 2% of nickels being used in batteries, especially lithium-ion batteries, but that has been increasing. And it's also an important chemical catalyst for hydrogenation of vegetable oils, reforming hydrocarbons, producing fertilizers. So scarce critical metal number 2 is copper. Copper is a very important metal. It's malleable, easy to stretch out into very thin, flexible wires, which are essential in electricity. Copper is used in virtually all electrical wire, except for power lines, which are mostly made up with aluminum. Industrial uses of copper, electrical manufacturing, that's 2/3 of it, 25% in construction, a little bit in transport and other industries. From a clean energy perspective, copper is going to be needed for generating solar and wind power, electricity lines to deliver that. No, and we won't actually. Well, never mind. And then, of course, there's some uses in lithium-ion batteries. Also other things. Scarce critical metal use number 3 is zinc. Zinc is interesting because it forms a what's called a passivation layer when it's exposed to air. So that means it gets an oxide coating that stays put, doesn't flake off. So that's a stable layer. So a very important way to protect metals is to add a thin zinc oxide coating, which is called galvanization, I think after the Italian inventor Galvani. And this prevents steel and iron parts from rusting. And it also offers some additional advantages in providing a longer life of galvanized industrial steel parts, increasing the durability, and increased cost effectiveness because it doesn't require any additional surface preparation such as painting or coating. And then it's also used as electrodes for zinc ion batteries. I haven't heard much about them, but your book says they're safer, cheaper, and longer lasting than lithium ion batteries. Zinc compounds are important for a wide range of other industries and in medical devices, and is thought to be environmentally safe. Scarce critical metal number 4, lead. More than 90% of global lead production goes into manufacturing acid storage batteries, with most of the rest going into solar panels and silicon wafers. Lead alloys are used in ammunition, pipes, cable coverings, building materials, solder, a lot of other things. And prior to the 1980s, organic lead compounds such as tetramethyl and tetraethyl lead were used as anti-knock additives and octane boosters in gasoline, but environmental concerns resulted in the gradual phase out of lead additives in gasoline, but they're still being used in some high octane fuels in the aviation industry for piston engine propeller aircraft. But it's just much smaller use of lead in fuel than used to be. Oh yes, Clint.
And I would just like to point out that UT Dallas played a little part in that.
Okay.
In the research on lead in the air and how it gets into your body.
Oh, you're talking about Dr. Manton's studies of lead in humans, sort of thing. Yeah, that's true. All right, so scarce critical metal use, we already did that. Cobalt, scarce critical metal number 5. It's a strategic metal because more than 60% of the global reserves are in the Democratic Republic of Congo. We've talked about that, the problem there. It's a metal that's has unique properties, so there's limited options for substitution. And almost all of these substitutes result in reduced product performance. And it's mostly used in ally constituent or chemical compound. And it's used widely, 30% in batteries, 20% in super alloys and magnet alloys, 10% in chemical catalysts, 13% in cemented carbide, glass and steel making. And in the clean energy transition, the larger use is in rechargeable batteries. Modern lithium-ion batteries contain up to 60% of cobalt as lithium cobalt oxide. So, people focus a lot on lithium in the clean energy transition, but cobalt is just as important. So lithium is the next one. And there's two major segments in the lithium market. There's mineral concentrates and lithium compounds and metal. Lithium-bearing minerals such as spodumene, which is a lithium pyroxene, if you will, and petalite, which is something else, are used in the ceramic and glass industry as a flux or glaze. And there's approximately 200 lithium-based chemicals, including lithium carbonate, lithium chloride, lithium bromide, lithium hydroxide, are used as greases and lubricants. It's important in air conditioners and in concrete and lithium alloys. They don't include in here the fact that lithium is useful as a pharmaceutical to help some mental issues. So one of the big uncertainties about lithium is how important is it going to be in the future during the 21st century. The current oversupply and the advent of sodium-ion batteries have seen demand fall in 2024. I really haven't heard that much about sodium-ion batteries yet, but we're going to need, as we move into the clean energy, solar and wind, we've got to have more battery storage. And the question is going to be one of how are we going to store it? Is it going to be lithium-ion batteries or what? So the last one of the scarce critical metals is gallium. It's a dispersed chemical trace element. There are no existing gallium mines. Instead, it's a byproduct of aluminum and zinc production. It's essential for the semiconductor industry. It's also alloyed with other metals such as zinc, selenium, indium, and antimony because of its low melting point. And importantly, it's got some unique properties. It's not replaceable by other metals for its current technological applications. All right, so let's talk about the rare critical metals, right? Molybdenum, tin, tungsten, antimony, thorium, uranium, and rare earths. So those three, SN, W, and SB, that always confused me. But SN is tin. You can tell that because it's got an N in it. And SB is antimony. You can tell that's antimony because that's short for stibnite. SB is pretty much the only antimony-bearing mineral. W for tungsten is another puzzler, but it's because the main mineral for that is wolframite. So anyway, these elements and the rares all have low abundances in the continental crust from less than 10 ppm to 1 ppm, and we get into these deposits in chapter 6. All right, so here we are, the rare critical elements, right? Sort of moving down the periodic table: germanium, arsenic, tin. They moved antimony over there, molybdenum, bunch of things. All right, there's 8 of them. Let's talk about the first one, molybdenum. It's mostly used for alloys in the steel industry and stainless steel, and then subordinate use, chemical catalysts and lubricants, pigments, and fertilizer. Molybdenum is used to increase the strength, hardness, electrical conductivity, and resistance to corrosion and wear in steel. So these are called moly steels: engine parts, heating elements, drills, saw blades. So iron moly steels are essential for railway tracks because of their strength and elasticity. It's used in circuit boards, lubricants and catalysts in the petroleum industry, corrosion-resistant pigments, and as fertilizer for some crops, including cauliflower and beans. Don't ask me why. Number 2 is tin, SN, mainly used for production of lead tin alloys, which are as commonly known as solder. And then also tin alloys with copper to make bronze. Chemical industry uses about 17% tin compounds. Tin is used for tin plates where metals like iron or its alloys are, yes, Clint.
Just going back to molybdenum being taken up by plants, little known gross fact, that's what caused the mass starvation in Iceland after the Skeftar fires eruption of 1783 was plants took up molybdenum, sheep ate it. The Icelanders depended on sheep, and then they got molybdosis. And in fact, I think the sheep got molybdosis and died because it replaces copper in your metabolism. So good for railroad tracks, don't eat it.
Interesting. No, little known fact. Thank you. Apparently it's used in tin plates, which are associated with walling, roofing and walling material.
And Brewer
lead
rabbit.
acid. What's that?
And Brewer rabbit. Tin plates to eat out in.
Oh, tin plates. I see what you're saying. Yeah. Well, and then there's always Tin Pan Alley. I never understood what that was, but apparently there was, I don't know why they call it Tin Pan Alley for the musical place, but anyway, lead acid batteries, and also in a wide range of other things that are high tech. Antimony is mainly used as a fire retardant in ball bearings, startup neutron sources in nuclear reactors. It's dopants in silicon wafers in the semiconductor industry, safety matches, brake pads, ammunition, and other things. And this is one of these elements that hit the news because, you know, China banned antimony, so you get some interesting things in the news media. This was in June. U.S. battery makers declare national emergency after China's antimony ban. And, you know, here's an example, you know, what's going on? Did they ship so little because they're running out or because they're trying to make a political statement? And this is where, you know, they may say one thing and it's the other thing. So people have to know something about that. So here's another one, another article in a journal called the National Interest on antimony. So tungsten it also has a wide range of applications. It has the highest melting and boiling point of all chemical elements and a very high tensile strength. Used a lot in the steel industry. So many of these other metals are used as alloys in steel, in jewelry, aerospace and aeronautical industries, parts, car industry, arc welding, permanent magnets, the military, explosives, chemical industry. You can see it has a wide range of applications. The next one are what we call the PGEs. So these are what we call the platinum group elements, which consist of platinum, palladium, rhenium, ruthenium, iridium, and osmium. So there's 6 PGEs. They're chemically very similar, but their physical properties vary considerably, and they're all considered as strategic metals because 90% of the world PGE reserves are found in the Bushveld complex. There comes the Bushveld complex again. And they have high melting points, very corrosion resistant, and catalytic qualities. I think, you know, everybody's heard about thieves getting under their cars and stealing their catalytic converters for the platinum in those converters. So there's a wide range of uses there. And another one is thorium. Thorium is radioactive. It's used an ally with magnesium to increase strength and creep resistance at high temperatures. Used as a catalyst in the chemical industry. Used in thoriated welding rods that are mostly made of tungsten. And there is apparently starting to be some interest in using it as a nuclear fuel. The people have been talking about it for a while. Now, there's one new thorium reactor in China which generates about 2 megawatts. that's not very much. So the Comanche Peak power plant, nuclear power plant, 2 units sort of southwest of Dallas-Fort Worth, those nuclear power plants put out about 2,500 megawatts. So a 2 megawatt plant is interesting from the point of view of, is that scalable up to be something that would really contribute to the grid? 2 megawatts by itself is peanuts. And then uranium, of course. Slightly enriched uranium is used mainly in nuclear reactors to produce electricity. That nuclear energy has gone up and down, and now it looks like it's coming up again. And also the military uses uranium-235, obviously, for nuclear weapons, and depleted uranium, which is enriched in uranium-238 for armor-piercing artillery shells. So interesting uses there. And then finally, we have the rare earth elements. These are sometimes called the lanthanides, or we can call them the rare earth elements, or the REEs. There are 15 elements, which includes lanthanum to lutetium, and as well as the elements scandium and yttrium, which have similar chemical behavior to the lanthanides. And the demand for rare earths increases every year. They're all +3, but they show a decreasing atomic radii with increasing atomic numbers. That's called the lanthanide contraction. So that the light rare earths, the LREEs, have a larger atomic radius. The heavy REEs, or HREEs, have a smaller atomic radii. And so because of these slightly different atomic radii, they have slightly different, behave slightly different. They have unique magnetic, phosphorescent, and catalytic process properties. They're used in a wide range of electrical and electronics, computer disks, cell phones, flat panel TVs, LED light bulbs, high-strength magnets, metal, laser equipment, a whole bunches of things. Now, the auto industry is using them especially as magnets in hybrid and electric vehicles. The rare earths are going to be very important in the energy transition. They're also important in wind turbines, also making them important in the energy transition. And then plenty of uses in medical. And of course, the military is very interested. So here we've got all of the important uses of the rare critical metals out of your book. All right, now let's go to the trace critical metals. And there's only 4 of them. And the first one is selenium. I should probably remind what the definition is: between 0.1 and 1 ppm in the continental crust. So that's like 100 parts per billion to 1 part per million in the continental crust. Selenium is used in the glass industry, the steel industry, the rubber production, petrochemical industry, electronics, electrolysis, batteries, chemical alloys, solar panels, pharmaceuticals, and agriculture. And then the second trace critical metal is cadmium. It's used in batteries, for example, rechargeable NiCad batteries, alloys, electronics, petrochemical industry, solar cells, spectroscopy, and nuclear technology. The third one is indium, which is used in electronics, computer industry, alloys, solar cells, nuclear technology, and medicine. And the last one is use in solar panels. Tellurium, and it's used in solar panels, cadmium, tellurium solar panels, thermoelectric materials, semiconductors, electronics, chemical industry, paints and pigments, and alloys. So there are the industrial uses of the trace critical metals. And that brings us to the precious metals, which are shown here as silver and gold, right? There in the red box. have the precious metals in this category down here. So gold is one of them, and as we know, no other metal has ever been held in higher esteem through history. Almost every historic empire using gold to symbolize power and accomplishment. I think our present president, the White House, is a demonstration of his commitment to honoring the tradition of gold in history. So interestingly, the first gold coin was minted only about 3,000 years ago, and it was King Croesus of Lydia, 560 BC. We use gold for jewelry, investment in currencies, electronic industry, aeronautical and space technology, and medicine. Yes, Clinton.
And if you've ever heard the expression "rich as greases," that's rich as greases.
Oh, that's greases, huh? I never heard that saying, but that explains it. Increasingly, I mean, gold can be drawn into wires, hammered into sheets, cast into ornate shapes. It's very soft, and so it's normally alloyed with other metals such as copper, silver, platinum to increase its durability. That's what 24 karat gold is pure gold, and then less than 24 karat is talking about how much of the other metals have been added to it. So investors consider gold as a way of safeguarding the value of their portfolio. We're seeing a lot of that now. The price of gold has basically doubled in the last year or so. Is that right, John? And John tells me that this is because investors are nervous about the value of the dollar. Electronics industry uses gold in almost every yes, Clint.
And I don't know if you pointed it out already, but it's one of its principal values is that it is pretty much inert.
Oh yeah, now that was why it was one of the first metals used, is because there was the processing that you had to do was minimal compared to, say, iron or something like that. We sort of went over that in sort of the early first lectures. And then cockpit windows are dusted with gold nanoparticles to reflect sunlight. It's used as lubricant between mechanical parts in space, and in medicine, it's still used as an alloy for implants. Silver is the other one that the book talks about in this chapter. Silver offers unique is physical strength, brilliance, malleability, ductility, electrical conductivity, as well as antibacterial qualities. The main uses of silver are in jewelry, 85%, investment, batteries, electronics. Well, we got batteries in there twice. We must be important. Okay, so that's there we've got the table and for silver and gold. And that's the end of that lecture.